Hi friends, welcome to my channel. In this tutorial session, I am going to show you some examples on rapidly varied flows. When we say rapidly varied flow, there is a rapid variation in flow depth and velocity in a short reach of a channel. So we have some learning objectives on this topic. So you have learning objectives. By the end of this chapter, you will be able to determine the amount of energy dissipated in water flowing over dams, weir, and other hydraulic structures. Just meet this presenting, prevent the scouring of channels downstream from the structures. And also you will be able to examine rapid change of flow regime from supercritical flow to subcritical flow in a short reach of a channel. So when we say short reach of a channel, there is abrupt change in the slope of the channel. You may have some drop, or sometimes if you have sluice gate, then there is a change in flow region. So we will just determine the Froude number of the flow just before the jump. If it is supercritical, then it will be just change it to subcritical flow. So you have some flow regime change. So, and you will be able to measure again the flow rate passing over hydraulic structures. So you may have hydraulic structures such as just spillway. Sometimes you may have just sluice gate, etc. And also you will be able to analyze how to recover the head or rise the water level or the downstream side of the measuring flow, and then thus maintain high water level in the channel for irrigation purpose or other water distribution purposes, maybe irrigation distribution network, or sometimes water supply, etc. So let's go to the examples now. So the example 4.1 is just a hydraulic jump. A 3-meter wide rectangular channel carries 15 meter cube per second of water at a 0.7 meter depth before entering the jump. Compute the downstream water depth and the critical depth. So you have depth before the jump, which is this one. This is the depth which is before the jump. Then what will be the sequent depth if you have flow rate given, and the width of the channel given. So you have depth again, you have then what will be y2. So to compute this, you have to calculate the nature of this flow just before the jump. Let us see. So the first step is discharge intensity. You can compute since it is rectangular channel. So you may have capital Q over B. Then this is discharge intensity. Then critical depth for rectangular channel is given by Q square over G the whole 1/3, which is 1.366 meter. This is the critical depth. Then V1, just the velocity, which is on this one before the jump, will be Q over D1, which is 7.14 meter per second. And what will be the Froude number before the jump? V1 over square root of G times Y1 for rectangular channel. Then you have 2.72. This is just greater than 1, so it is just supercritical flow. So for supercritical flow, this is just the proof how to calculate the velocity, which is Q over Y for rectangular channel. You have Q area times velocity, then instead of area, B times Y. Then just capital Q means small q, just discharge intensity means just you have Q over B, which is just this discharge, which is this one. Then Y times V, which is this one. Then finally, if you divide by B, then finally you get this one. This is for rectangular channel. For other channel, it will not work. So you have this is greater than 1. So since this is greater than 1, supercritical flow is upstream channel. Then there is jump formation. So jump will be formed. Then you have hydraulic jump equation. This is Y2 over 0.7 is equal to 1 over 2 square root of 1 plus 8 F1 square minus 1. Then you get this is the depth or the downstream water depth, which is the post jump. Okay, second example is a rectangular channel of open just 3 meter wide carries a discharge of 15 meter cube per second. The channel slope is given, which is this one, 0.004. This is the bed slope. and Manning's roughness 0.01. At a certain point in the channel, the flow reaches normal depths or uniform flow depths. Then determine the state of flow. So you are asked the state of flow, whether subcritical or supercritical, depending upon Froude number before the jump. If a hydraulic jump takes place at this depth, what is the sequent depth at this jump? What will be the second depth or post jump? Estimate the energy head loss through the jump. So given parameters, you have bottom width of the channel, which is 3 meter, and discharge is 15 meter cube per second, and bed slope given 0.001. Then Manning roughness is also given. So from this, you have Manning equation. Using Manning equation, this one, where just dn is normal depth of the channel, then you can calculate the normal depths. So this is just a cross section of the channel, and this is the alignment or just section of the hydraulic jump. This is the jump, which is initial normal depths before the jump. Then you have to calculate the state of flow here. Then if there is supercritical flow, then there is jump formation like this. Then what will be y2? Now let's calculate. You have Manning equation, this equation. Then finally, by try and error, you will just calculate the normal depth, which is 1.08 meter. By try and error, you have D1, which is this one. Then once you get D1, then V can be computed. So V will be just V1 will be this one. Just you just Q divided by area, Q divided by area will be V1. Then finally, after computing the velocity, this one, the velocity in this reach in section 1, then you can calculate Froude number. So Froude number is V1 over square root of GY1 for rectangular channel. Then you have 1.42, which is greater than 1. Supercritical flow. So jump will be formed then according to hydraulic jump formation formula, D2 divided by D1 equal to 1 over 2 square root of 8F1 square minus 1. Then D2 will be, this is D2, second depth or post jump. And the change in energy, you have E1 minus E2. So this expression is nothing, just the specific energy in section 1, and this is the specific energy in section 2. So the change in energy, E1 minus E2. So this is the change in energy. You have to compute the velocity in the second section. So you have Q is constant, divided by 3D2. Then this is the velocity in section 2. Then change in energy means E1 minus E2. Then this is the change in energy. The change in energy. Okay, example 4.3 is head loss and energy dissipated. So water discharging into 10 meter wide rectangular horizontal channel from a sluice gate is observed to have undergone a hydraulic jump. The flow depths, which is just the upstream before the jump, the flow depths and velocity given. So the flow depths before the jump 0.8 and the velocity v1 given 7 meter per second. So these are the given parameters. This is the sluice gate. You can see this is the sluice gate. So initially we have some water depths here. Then it is just discharging out. Then what will be the flow depths and the Froude number after the jump, and the head loss and the energy dissipation ratio, and the wasted power production potential due to the hydraulic jump also. What will be the power just wasted due to this jump? Now, given parameters, you have B 10 meter width of the channel, and Y1 you have 0.8 before the jump, and V1 7 meter per second. According to this given sketch, required what will be Y2, F2, HL, and energy dissipation ratio is head loss divided by energy 1, and power wasted, mechanical power wasted due to the jump. Now let's go. Froude number is given by this equation. This is a general equation. V squared divided by square root of G times D, where D is the hydraulic depth, which is area divided by top dimension, and V1 over square root of GY1 for rectangular channel. then you get this result. After substitution, you get 2.5, which is greater than 1. So it is supercritical flow. Then jump will be formed. Then you can calculate the other parameter. Since jump will be formed, the sequent depths can be computed as using this equation: y2 over y1 equal to 1 over 2 times -1 plus square root of 1 plus 8 f1 square. So if you substitute, then y2 over y1, then you get y2 will be 2.46 meter. So this is the post jump in section 2. And from continuity equation, Q is equal to A1 times V1 is equal to A2 times V2. Then V2, we can calculate V2 Y1 over Y2 times V1. Then we get, this is the velocity in section 2, which is 2.28 meter per second. So once you compute this one, then you can calculate the Froude number at section 2. At section 2, V2 over square root of G Y2. So this is 0.464. This is less than 1. Then it is subcritical flow. So this is the main objective of this topic, is just changing supercritical flow to subcritical flow, so that the downstream riverbed will not be damaged or just will not be scarred due to erosion. So the head loss can be determined now, just E1 minus E2. Using this equation, you can find, or you can use this equation. This is general equation. You can prove from energy equation. Then let us calculate. So head loss will be this expression will be 3.297 and 2.724. If you calculate the difference, then this is the head loss dissipated due to the jump. Then energy dissipation ratio, let's calculate. The energy dissipation ratio is nothing, head loss divided by E1. Since E1 we have, then if you divide head loss divided by specific energy at section 1, you get this one, 0.173, which means 17.3% of the available head or mechanical energy of the liquid is wasted or converted to thermal energy as a result of frictional effects during this hydraulic jump. So just if you go further, then the mass flow rate, which is in kilogram per second, is just rho times volume flow rate, which is rho Q, then just rho times A1 times V1. So this is the mass flow rate of water, which is 56,000 kilogram per second. Then the power dissipated corresponding to the head loss, this one will be just the mechanical energy which is dissipated due to the jump, is mass flow rate times gravity times head loss. If you multiply, then you get this one. This is just in Newton meter per second, which is kilowatt. You can convert into kilowatt, which is 314.78 kilowatt, which is mechanical energy wasted due to the jump. Or simply, you can use this equation: power wasted is equal to rho G Q times head loss. If you multiply this one, you can find in what again? 1000 times 9.81 times Q flow rate. You have Q flow rate, which is given. Then this is 10 times 0.8 times 7. Then finally, this is just the flow rate, which is area times this one, rho A V1, which is area 1 times V1. Then finally, this is the discharge, this is area. Then finally, you have, this is the head loss. Then you can find the same result, which is 314,783.28 watt. Then you can convert into kilowatt. Okay, this means that if water is routed through a hydraulic turbine instead of being released to downstream side of the channel, just from the sluice gate, up to 314 kilowatt of power could be generated. But this potential is converted to useless thermal energy to the downstream side. Useless thermal energy instead of use of power, just causing a water temperature rise of this one. So water temperature rise is given by this equation, which is energy dissipated divided by mass flow rate multiplied by just Cp or fluctuating pressure coefficient. So you have 314 kilojoule per second divided by mass flow rate already computed. Then if you multiply by just fluctuating pressure coefficient for water, you take this constant, then this degree centigrade. Just you can finalize now. Hydraulic jump characteristics, just you have amount upstream flow is supercritical. That is pre-jump Froude number. If you have less than 1, ratio of height after to height before the jump will be 1. So descriptive of this jump or characteristics of this jump, no jump formation. If the Froude number is less than 1, you have no jump. Flow must be supercritical, or just flow must be supercritical for jump to occur, which is none. Otherwise, standing, which is between this one. Otherwise, if you have amount of upstream flow, which is supercritical, pre-jump Froude number, then you can have standing undulating wave, which is weak jump again, if this is the difference, and also oscillating jump. And if it is more than 9, clearly defined turbulent or strong jump. So these are just characteristics of hydraulic jump. We can just finalize now. So example 4.4 is just hydraulic jump from spillway. Let's see now from spillway what will happen. So water on horizontal apron of 30 meter wide spillway shown below has a depth of 0.2 meter, which is before the jump. You have this depth. This is just from spillway, it is just going with a velocity of 6 meters per second. Determine the depth y2 after the jump. What will be the depth y2 after the jump? The Froude numbers before and after the jump, F1 and F2, and the head loss due to the jump. So you have width of the spillway given. So the spillway may be like this, just the structure of the spillway may be like this, clear? Then just flow is going like this, clear? So this is the spillway, which is it could be OB or something. Then once you have spillway, then just you have overtopping, which is like this. Then downstream of the spillway, you have depths at this point with a velocity of 6 meters per second. You may put some chute blocks, just staggered. You can put baffle blocks, and sometimes you have apron. Then just to dissipate the energy, just flow must be going slowly, just to avoid erosion or scouring of the downstream river bed. So let's see now the calculation. So the first step is you have to identify the flow region in the upstream region. So the Froude number before the jump should be computed first. Let us calculate. F1 will be equal to have V1 over square root of GY1. So you have 4.28, which is greater than 1, which is supercritical flow. So jump will be formed. Then finally, the sequent depth Y2 after the jump can be found from this equation, hydraulic jump equation. Then after calculation, you get Y2 will be 1.11 meter. So this is the depth after the jump, which is the post jump at this point. Then, but once you know this, from continuity equation, we have Q is equal to A1 times V1 is equal to A2 times V2. Then V2 will be 1.08 meter per second. Now let's compute Froude number. We can compute in downstream V2 over square root of GY2. Then this is 0.327, which is less than 1. So the flow is changed into subcritical flow. So once you change the flow into subcritical, then you can find the energy loss. The energy loss or the head loss due to the jump will be, this is Y2 minus Y1, the whole cube over 4Y1 times Y2. Then you get this. So this is the energy, which is loss, 0.849 meter. Okay, so as exercise, we can try this exercise. Rectangular channel, you have rectangular channel. The head loss or the loss of energy head in the hydraulic jump is 4.25 meter. The Froude number just before the jump is this one, which is F1. Determine the depths, which is before and after hydraulic jump, Y1 and Y2 required. Discharge per meter width of the red channel. and the Froude number after the jump, F2, the mechanical power wasted and the percentage loss of energy head due to the jump, and the efficiency and the length of the jump. Clear? So given parameters, you have head loss and F1. Then required parameters, you have Y1, Y2. Then Q is equal to just discharge intensity equal to total discharge divided by the width of the channel. And F2 will be just asked then power, which is wasted due to the jump, And then you are asked the percentage loss of energy, which is this one, change in energy divided by E1. And you are asked again the efficiency of the jump. The efficiency of the jump is E2 minus E1. E2 minus E1. Then the length of the jump. Length of the jump, you can calculate length of the jump, which is L equal to, you have jump coefficient according to the nature of the flow. Jump coefficient, then you multiply by Y2 minus Y1. Y2 minus Y1 will be the length of the jump. What will be the length of the jump? So as highlight, just use this equation. For head loss, you will just use this one. But you are just given head loss already, you substitute here. Then F1, you have to substitute here. Then by rearranging the equation and solving simultaneously, you can arrive at a solution. And also you have hydraulic jump equation. Clear? Hydraulic jump equation, which is Y2 over Y1 is equal to 1 over 2 times -1 plus square root of 1 plus 8F1 square. Then under square root, then you just substitute instead of F1. Then you can solve by the three equations. Then you can arrive. Okay. Another exercise is a trapezoidal channel. If you have trapezoidal channel, how do you compute? A trapezoidal channel has a bottom width of this one. You have bottom dimension, this dimension given. Then side slope again M2. This is 1 to M already given, and it carries a discharge of 8.5 meter cube per second. So a hydraulic jump occurs in this channel. The flow depth just before the jump is 0.3 meter. This is the flow depth before the jump. Determine the depth after the jump. So given parameters you put, bottom widths M, Q, and Y1. Then require you are asked V1, F1, and Y2. Then as hint, area of trapezoidal channel is B plus My times Y. Clear? So since you have Y1, then you can substitute here Y1, then area of the channel you can find. Clear? So once you have area of the channel, you can solve velocity, which is Q over area. Already Q given here 8.5. Then Froude number you can find F1. This is F1. You can compute V1 over square root of G times D. G times D. This is hydraulic depth. So hydraulic depth for any channel is area divided by top dimension. So how do you compute? So top dimension for trapezoidal channel is B plus 2My. Because you have this one, you can just divide. Then My, you have My. Then B plus 2My. So this is top dimension. You substitute here. Already area computed. Then this is weighted perimeter. It is not required now, but you can solve hydraulic radius, etc. Then finally, you can just solve Y2 over Y1 using hydraulic jump equation. You substitute here, then you have F1, then you have Y1, then what will be Y2? So this Y2 can be solved. So this is as exercise. And exercise 4.3 is sluice gate and hydraulic jump. So a sluice across a channel 7.2 meter wide discharges a stream 1.2 meter deep. What is the flow rate when the depth of the water in the upstream of the sluice gate is 8.4? So you have depths from here up to here, depths of water, and on the downstream side, concrete blocks have been placed to create a condition for hydraulic jump to occur. So this is a chute block, which is water is going. Then this chute block is just to dissipate the energy. Then calculate the force on the blocks if the downstream depth is 3.6. So downstream depth given 3.6, and also before the jump also already given here, depth is given. Then it is simple. So So the only thing is you will use the three governing equations in open channel flow. These are continuity equation, energy equation, and momentum equation. So from continuity equation, you have section 1, section 2, and section 3. So you develop equation like this. A1 V1 is equal to A2 V2 is equal to A3 V3. Then V2 will be in terms of V1 you can find, and V3 again you can find like this. Then using this energy equation, you will use just the datum you can take at this point, then energy you can have. So since Z is the same for all, then Y1 plus V1 square over 2G is equal to Y2 plus V2 square over 2G. Then you substitute the same approach. Then since depth is given, then finally you can arrive at the solution. Then momentum equation, you can find momentum equation, summation of net force, summation of net force is equal to rho q times change in velocity. Rho times q, which is the mass flow rate, then the change in velocity between 2 and 3, you can find V2 minus V3, V2 minus V3, or sometimes you can find here just the pressure, which is just like this. You have to draw pressure distribution like this at this point, and also at this point you have the same, and at this point again you have. So you have hydrostatic, so just net force, the net force you have F, then finally you can compute this force. Okay, thanks for watching this video. If you have any question or doubt regarding this tutorial session, please write down in the comment section below. I will reply on it. Thanks again.